Okay, this is now the geometric design of highways. Now, in the geometric design of highways, it deals with the dimensioning of the elements of highways such as horizontal curves, vertical curves, cross-section. We have the track climbing lanes, bicycle paths, and parking facilities. Now, so let us start with the horizontal curves. So, first, we have your circular curve, or that is a simple curve. You try to take note that this is a circular curve, hence this is derived from a circle. Now, so the first thing that we should have to do is let us try to draw two tangent lines. So these are now your two tangent lines with the desired direction. So the direction of tangent lines may either be the azimuth is given or the bearing is given. Now, from the two tangent lines, let us try to connect a simple curve or a circular curve. So we now have your circular curve. Now, what are the elements of a circular curve? So let us start with the PC. So what is PC? So when you're speaking of PC, this is the point of curvature of the circular curve. So this point is where the circular curve leaves the tangent, or this is the start of the circular curve. So this is therefore the point where the circular curve starts, or the point where the circular curve leaves the tangent. Now, another element of a circular curve is now your PT. So, what is your PT? So, the PT is known as the point of tangency. So, this is therefore the point where the circular curve meets the tangent, or this is now the end of the circular curve. Now, another element of a simple curve or circular curve is now your PI. So we now have your PI. So your PI in here is now the point of intersection. We have the point of intersection of the two tangents. Point of intersection of the two tangents. Or this point of intersection is also known as the vertex of the simple curve. Of the simple curve or the circular curve. So that is now your PI. Now, another element of a simple curve is now the tangent distance. And let us consider that one as T. So this is therefore your tangent distance of the circular curve or of the simple curve. So this tangent distance is of course measured along the tangents. So if this is now the tangent distance. So this is equal to t. Let's consider this is now the tangent distance, which is equal to t. Also, this one in here up to pt is the tangent distance. Now, so in the tangent distance, we have the back tangent and we have the forward tangent. Okay, so what is this back tangent? Okay, so the back tangent, this is the distance along the tangent. So we have the distance along the tangent from the PC to the PT. From the PC to the PI. From the PC to the PI or to the vertex of the simple curve. So this point PI or the vertex of the circular or that of the simple curve. Long chord. Another element of a simple curve is now the external distance. So we now have E as the external distance. So what is therefore this external distance means, or what does external distance means? So this is the distance. So we now have the distance drawn. This is drawn from the PI or the vertex of the curve to the midpoint of the circular curve. So we now have the midpoint of the circular curve. So if you try to look at now the midpoint, so if you try to take a look at this point, so this is, I'm just going to draw a line in here. Okay, so your external distance in here is now the distance from the PI or vertex to the midpoint of the circular curve. This is therefore the external distance. Now, another element of a simple curve is the middle ordinate. And let's try to denote that by N. So that is the middle ordinate. So what is this middle ordinate? So it is the distance drawn. The distance drawn from the midpoint of the curve, from the midpoint of the curve to the midpoint of the long chord, to the midpoint of of the long chord. Okay, so if you try to look at now the figure, this is the midpoint of the circular curve. So from the midpoint to the midpoint of the long chord, so this is your long chord, that is now your middle ordinate. Now, another element of a simple curve is the radius. So you have now your arc, or this is therefore the radius of the circular curve. Or the radius of the simple curve. This is therefore the radius of the simple curve. Now, another element of a simple curve is now your capital D. And your capital D here is the degree of the curve. So this is therefore the degree of the circular curve. Now, so for the degree of a circular curve, one full length station, degree of the circular curve of a full length station. So that is a full length station. So what is a full length station? You try to take note in here that one full length station is equal. So this is equal to 20 meters. So that is one full length station, which is equal to 20 meters. Okay, so what are the necessary formulas for a simple curve? Now, let us try to consider one in here is using now your arc basis. So we now have your arc basis. Let us try to consider one full length station. Okay, so if this is now your circular curve, let us try to consider one full length station. So this is now circular curve that we are going to consider. So one full length station. And we define that the angles subtended by a one full length station is the degree of the curve, which is equal to D. Okay, so this is now your D. And this is now the radius of the circular curve. So if you try using the arc basis, this means to say that the length of this arc or length of the arc is equal to 20 meters. So from this point up to that point. So that is equal to 20 meters. Now, if we are speaking of a full length station, it is divisible by 20. Now, let us try to determine now the relationship between the degree of the curve and the radius of the circular curve. Now, let us try to extend this arc in here. So, we form now a circle. So that if you will going to get ratio and proportion. So, Russian proportion, you have now 20 S to D is now equal to the circumference of the circle. So, we have now the circumference of the circle is to 360 degrees. Okay, so one revolution in here is 360 degrees. So that is. Now, so that your 20 S to D is now equal to the circumference of a circle is equal to 2 pi r. That is 2 pi r all over 360 degrees. So that if you try to get now the value of D, this is therefore equal to, so we have 20, multiply this by 360 degrees all over 2 pi r. Now, you try to take note that the unit of the degree of the curve is in degrees. 20 is in meter. The radius is supposed to be in meter. So they will cancel out. So the unit left in here is degrees. And therefore, 20 multiply this one by 360 degrees all over 2 pi. And that will now going to give you 1145.916 all over r. So the degree of the curve is now equal to 1145.916 all over r. Kastamitin. All over r. Ada mo di siya yung kataman data. Ano naka? Okay, so we now have the degree of the curve, 1145.916 all over r, or your r in here is now equal to 1145.916 all over the degree of the curve. Okay, so by this time, we'll be using SI units. So if you have, if the station, so you have a station or stationing of a certain point on the simple curve is equal to 1 plus 0, 0, 0. What does this mean? So this means 1 kilometer and 0 meter. If you have 3 plus 0, 1, 4, so this means to say that this is, or that is 1,000 meter. So if your stationing is 3 plus 0, 1, 4, this means to say 3 kilometers and 14 meters. 3 kilometers and 14 meters. So in other words, this is equal to 3,014 meter. Now, if your stationing is 10 plus 220.35, this is 10 kilometers. You try to take note that stationing has always been based from the origin. So you have from the from station 0 plus 0, 0. This is 10 kilometers and 220.35 meters. So in other words, this is 10,220.35 meters. let's now proceed in determining the relationship between D and R using now the chord basis. So again, let us try to consider one full length station, whose chord length is 20 meters. Now, so let's try to have now the chord length in here is 20 meters. So we have one full length station. So this is therefore the arc supposed to be. In the arc basis, we deduce an arc length equal to 20 meters. So by this time, let us try to consider a chord length of 20 meters. So this one in here, the chord length is now equal to 20 meters. This is now your degree of the curve, and this is the radius of the simple or the radius of the circular curve. Now, if you try to bisect this one full length station, so let's try to bisect this one full length station now such that this one in here is now equal to d over 2, and this is also equal to d all over 2. Hence, this is 10 meters and another 10 meters. Now, let us try to get this one in here. So if you try to take a look this point now, okay, in an exaggerated manner, so we now have considered the half of the full length station. So we now have the half of the full length station. So this is therefore your point O, and this one in here is now your 10 meters. And this is equal to d all over 2. This is the radius of the circular curve or that of the simple curve. So if you're going to get sine of d over 2, sine d over 2, so the sine d over 2 is now equal to the opposite side, which is equal to 10 meters all over the radius, which is the hypotenuse. So that your R in here is now equal to 10 all over sine of d all over 2. So this is therefore the relationship of D and R using the chord basis. Again, you try to take note that in most problems, if not specified, that you are using a chord length of this much, then you have to use the arc basis, because the arc basis is more accurate than your chord basis. Usually, they're just using the chord basis in the field. Next, let us try to consider the circular curve. So we have now your PC, your PP, and this is now the radius of the circular curve. Now, the central angle of the circular curve is equal to I. Now, from the circular curve, let us try to get one full length station. So this is now your one full length station. And for a full length station, the arc length is equal to 20 meters. So this is equal to, from that one, is equal to 20 meters. So from this point up to this point, that is now the length of curve. So from this full length station, the included angle is equal to D. So that is the included angle. So again, if you try to use again ratio and proportion. So ratio and proportion, 20 is to D is now equal to the length of curve, which is LC is to I. And therefore, the length of the circular curve or the simple curve is equal to 20 I all over D. So that is how we determine the length of the circular curve or the length of. Now from the circular curve, let us try to consider triangle OPC and PI of, or the vertex of the circular curve. Now such that this angle in here is I over 2. So this is also equal to I all over 2. This is now your I all over 2. Now since the circular curve is tangent, okay, to the tangent distance, then this is therefore equal to 90 degrees. Now if you try to get tangent of I all over 2, so this is now tangent of I all over 2 is now equal to, opposite is now the tangent distance all over the radius of the circular curve. Hence, the tangent distance of a circular curve is now equal to R tangent I all over 2. Now still, let us try to consider triangle OPC and PI. So if you try to take a look now, this is therefore the circular curve. So if this is the circular curve, from the vertex to the midpoint of the circular curve, we call this one as the external distance. And from the origin of the circular curve to the midpoint of the curve, that is still the radius of the circular or the simple curve. So from this triangle in here, if you try to get cosine of I all over 2, so cosine I all over 2, so cosine I over 2 is equal to the radius. Okay, so it is equal to R all over, so adjacent side all over the hypotenuse. And the hypotenuse in here is now equal to R plus E. That is R plus E. So we now have R plus E. We have cosine of I all over 2 is now equal to R. So we have R cosine of I all over 2 plus E cosine of I all over 2 is now equal to the radius. So we have E cosine I all over 2 is equal to R minus R cosine I all over 2. So your E in here is now equal to, factor out R, so that is 1 minus cosine I all over 2. All over, so we have to divide this one by cosine I over 2. So this is now your cosine I all over 2. Middle ordinate. Now, the back tangent and the forward tangent of a 4-degree circular curve have azimuths of 220 degrees and 280 degrees respectively, intersect at station 10 plus 032.15. Determine the elements of the simple curve or the circular curve. Now, so I'm just going to write the given in here. So we have given in here. So we have the degree of the curve is equal to 4 degrees. So we have the back tangent azimuth. Back tangent azimuth is 220 degrees. So we have the forward tangent azimuth is equal to 280 degrees. So they intersect at station PI, or that is now the vertex of the circular curve, which is at station 10 plus 032.15. So let us try to determine now the elements of the simple. Now, so first, let us try to draw the tangent lines. So we have now the tangent lines in here. So the azimuth in here is, so this is now your north in here. So the azimuth is reckoned from the south going clockwise. So we have 220 degrees. And 220 degrees, somewhere else, this point. So this is equal to 180 plus 40. So we have 220 degrees. Okay, so this is now azimuth of the back tangent, which is equal to 220 degrees. Now, the azimuth of the forward tangent, so let's try to determine now the azimuth of the forward tangent. And the azimuth of the forward tangent is equal to 280 degrees. So this is reckoned from the south again. Reckoned from the south going clockwise. So this is now 280. So that is 270. Hence, this is equal to 280 degrees. So this is 280 degrees. Now, let us try to connect these two tangent lines by a circular curve. So let us try to consider that this is now the PC of the circular curve. So that is the tangent distance. And this point in here is now the PI, or that is the vertex of the circular curve. So we have the tangent distance on this side of the PC should be equal to the tangent distance on this side of the PT. Because this is a circular curve, so symmetrical siya. Now, okay. So this is now your PT, or that is the point of tangency. So let us try to connect now the two tangents with a circular curve. So that is therefore the circular curve. Now we now have the radius of the circular curve. So this is now the radius of the circular curve. So first in here, let us try to determine your angle of intersection, and that is the deflection angle of the forward tangent, or that is the central angle of the simple curve. Now, this tangent is 220 up to that point. So that is 220 degrees. Hence, your I is now equal to, so we have 280. So from here up to that point is 280 minus 220. So that is therefore the deflection angle of the forward tangent, or the central angle of the simple curve. And this one is equal to 60 degrees. We are now ready to determine the other elements of the simple curve. So what are the other elements of a simple curve? So we now have your R. So your R in here is 1145.916 all over the degree of the curve. And this is equal to 1145.916 all over the degree of the curve is 4 degrees. And your R therefore is equal to, we have 286.479 meters. We are now ready to determine the tangent distance of the circular curve. And the tangent distance of a circular curve, your T, is equal to R tangent I all over 2. So this is equal to, your R in here is 286.479 meters tangent of 60 degrees all over 2. Hence, the tangent distance is now equal to 165.399 meters. So that is therefore the tangent distance. Let's try to proceed now to the other elements of the simple curve. And that is now the length of curve. So the length of curve, or that is the length of the simple curve or circular curve, is equal to, so that is 20 I all over D. That is equal to 20, your I is 60 degrees, all over the degree of the curve, which is equal to 4 degrees. Hence, the length of the curve is equal to 300 meters. Now, another element is the long chord. So, we now have your long chord. So, the long chord, which is equal to C, and this is equal to 2R sine I all over 2. So that is now your C is 2R all over sine I all over 2. And this is therefore equal to 2. Your R is 286.479. That is now sine of 60 degrees all over 2. So that the long chord is therefore equal to, so the long chord is equal to 286 point, that is 286.479 meters. So that is the long chord of the simple. Another element of the simple curve is the external distance. So the external distance, so let's try to label this one in here. So we are through with the tangent distance. We are through in determining your I. So this is now your length of curve. So we have the long chord, and this is now your long chord. And the long chord, which is equal to C. So let us try to determine now the external distance. So we now have the external distance. So this is therefore external distance again from that point to the midpoint of the circular curve. So that is the external distance E. So how are we going to determine now the external distance? So the external distance E is equal to R, we have secant, I all over 2 minus 1. So this is therefore equal to, what is again the radius of the circular curve? 286. So that is 286.479. We now have secant. I in here is equal to, so we calculated your I, that is 60 degrees. So secant of 60 degrees all over 2 minus 1. So the external distance is equal to 44.318 meters. So another is the middle ordinate. So again, the middle ordinate is the distance from the midpoint of the curve to the midpoint of the long chord. So this is now denoted as N. And the middle ordinate is equal to R, that is 1 minus cosine I all over 2. So that the middle ordinate is R is 286.479, 1 minus cosine of 60 degrees over 2. So we now have the middle ordinate is 38.381 meters. Also, let us try to determine the stationing of the PC and the PT. Now, given is station of the vertex or the PI of the curve. So they intersect at station. So we have 10 plus 0, 3, 2.15. So we go to the PC to determine now your PC, station PC. So we have to subtract your tangent distance. If you try to subtract the tangent distance, so the tangent distance is 165.399. So if you try to subtract the tangent distance, we get station PC. And station PC is now equal to 9 plus 866.751. So this is just the same as that. Okay, if you have, so this is 10,000, 0, 3, 2.15, subtract 165.399. So if you try to subtract that one, this is 9866.751. So this is 9 plus 866.751. Because you try to take note that in stationing, okay, so this is per kilometer. So this is 9 kilometer and 866.751 meters. And then, let us try to determine station PT. So if you try to get station PT, we have to add the length of the curve. And the length of the curve is equal to 300. And this is therefore your station PT of the circular curve. So this is 10 plus 166.751. You try to take note that if station PI or the vertex of the circular curve is given, and you are required to determine station PC and PT, knowing now the tangent distance, do not go from station vertex plus the tangent distance is equal to station PT. Because stationing of the circular curve or the simple curve always start at the point of curvature. So you have to go to the point of curvature, going to any point along the circular curve or arc of the circular curve. Okay, so we now have the second problem. A 4-degree circular curve joins the tangents, making an angle of 38 degrees. So the angle of intersection is equal to 38 degrees. It is necessary to bring the middle point of the curve 3 meters nearer the vertex. What changes are required in the points, are required in the radius and in the point of the curve? So we have your D here is equal to 4 degrees. So let us try to draw the tangent line. So we now have the back tangent. So this is the back tangent. And we now have the forward tangent. This is the forward tangent. Again, let us try to connect the two tangents with a circular curve or a simple curve. So this is your PC, this is PT, this is now your PI or the vertex of the circular or the simple curve. So the angle of intersection of the two tangents is equal to 38 degrees. Now, we have to draw now the radius of the circular curve. Okay, so there's your O, and this is now the radius of the circular curve. Now, let us try to denote the old curve are those elements with no prime. And the new curve, because we have to replace this original simple curve by bringing the middle point of the curve 3 meters nearer the vertex. This is also your I. Now, so for the old curve, so let's try to determine now the elements of the old curve. So for the old curve, let us try to determine now the radius of the old curve. And the radius of the old curve is equal to 1145.916 all over the degree of the curve. So this is 1145.916 all over 4. So this is equal to 286.48 meters. 286 6.48. That is 48 meters. So that is now the radius. So let us try to determine the external distance of the old curve. So this one in here is the external distance of the old curve. So your E is equal to your R, we have secant I all over 2 minus 1. So this is equal to, the value of R is 286.48. We have secant, your I is 38 degrees, all over 2 minus 1. So this is therefore equal to 16.51 meters. And the tangent distance T of the old curve. So your T is equal to R, tangent of I all over 2. So this is your R, is 286.48. We have tangent of 38 degrees all over 2. Hence, the tangent distance of the old curve is 98.64 meters. That is therefore the tangent distance. Now, let us try to replace this old curve by bringing the middle point of the curve nearer, 3 meters nearer the vertex. So let's try to bring this one 3 meters nearer the vertex. And therefore, this is now your 3 meters. And therefore, the new curve will therefore be this one in here. Hence, your E prime from this point up to that, we bring it. So we have your E prime in there. Now, such that for the new curve, then your E prime is now equal to, so we now have your E prime. So now, makita. So we have E is from this point up to that point. So that is your E of the old curve. So we bring this, and therefore, this is now your E prime. So that is the external distance of the new curve. So the external distance of the new curve is now equal to the external distance of the old curve minus 3 meters, because we have to bring the middle point of the curve 3 meters nearer the vertex. So this is now E of the old curve minus 3 meters. So this is equal to 16.51 minus 3, or that one is now equal to 13.51 meters. 13.51 meters. So let us try to determine now your E prime. So the external distance E prime is now equal to, we have the same equation, so that will be R prime. We now have secant I all over 2 minus 1. So let us try to determine now your R prime. So this is your E prime all over second I all over 2 minus 1. And this is equal to 13.51 over second, your I is 38 degrees all over 2 minus 1. Hence, the radius of the new circular curve is equal to, that is 234.46 meters. So that is the radius of the new circular curve. This is now the radius of the new circular curve. This is now your R prime. So this one is now your PC prime, and this is now your PT of the new curve, or that is now your PT prime. Now, let us try to determine now the tangent distance of the new curve. So this is the tangent distance of the new curve from PC prime to the vertex. And that is now your T prime. So that your T prime is now equal to R prime tangent I all over 2. So this is equal to 234.46 tangent of 38 degrees all over 2. Hence, T prime is equal to 80.73 meters. So we now have the changes in the radius of the simple curve. So that change in the radius of the circular curve is equal to the tangent distance of the old curve minus the tangent distance of the new curve. So T minus T prime. T minus T, the radius is the radius of the old curve minus the radius of the new curve. And this is therefore equal to the radius of the old curve is 286.48 minus the radius of the new curve, that is 234.46 meters. And therefore, the change in the radius of the circular curve is 52.02 meters. 52.02 meters. Now the change in the points of the curve. So we now have the change in the points of the curve. So the change in the points of the curve, that is the change in the points of the PC of the old and the PT of the old. And this is equal to the tangent distance minus of the old curve minus the new curve. So minus the new curve. So this is the tangent distance of the old curve minus the changes, minus the tangent distance of the new curve. And this is equal to, so we have 98 60.64, the tangent distance of the old curve, minus 80.73, and this is therefore equal to 17.91 meters. Hence, try to take note in here now, hence, the old PC and the old PT. Hence, the old PC and the old PT must be moved. So you have to move. Must be moved 17.91 meters towards the vertex. Okay.